The last topic we're going to look at in this lecture is logarithmic differentiation. Now, logarithmic differentiation is a technique that we use, first of all, to differentiate the log of a function instead of just the function itself. Now you might say, well, why would I want to do that? It looks more complicated. Well, actually taking the log of a function allows me to use all those simplification rules, and then it's easier to take the derivative. Not all the time, sometimes it's just easier to take a straightforward derivative, but a lot of times it does make it simpler. So we're going to make two cases here. Our first case is that you can take a derivative of a complicated expression a lot easier if you take the natural log of it. So let's look at an example where we kind of have a complicated expression. Let's look at the derivative with respect to x of the cubic root of x squared plus 2 over x to the 5th times x squared minus 1 to the 4th. Now this is a pretty complicated expression. Let's go ahead and rewrite it just a little bit before we take its derivative. And we're just going to do this the brute force method. We're just going to kind of pound and chug our way through this one. So this is to the 1/3 power x to the 5th x squared minus 1 to the 4th. I'm going to use a quotient rule with the product rule, chain rule. So let's go ahead and set this one up. We'll see how far we can get with it. So we have a quotient here. So the quotient starts with the bottom function times the derivative of the top function. Now I'm not actually taking that derivative in this step, I'm just writing out my steps. So again I have the bottom times the derivative of the top minus the top times the derivative of the bottom. Now this is the ugly piece, because when I take the derivative of the bottom, I have a product rule all over the bottom squared. Okay, so there's my start. And again, I haven't really even taken a derivative yet. I'm just kind of getting going here, kind of setting up the work. So let's go ahead and keep working. And this is complicated. The derivative with respect to x is kind of what I'm looking at right here. That's the piece I'm working on. So I take the 1/3 out front, I bring the exponent down, I decrease it by 1 unit, 1/3 minus 3/3 is a negative 2/3, and then I multiply it by the derivative within. Of course, and we keep copying down here. Now this next piece is where it's going to get a little complicated. I'm not going to set up the ddx again. I'm just going to go ahead and use the product rule on this. So I have the first function times the derivative of the second, which is the chain rule. You bring the 4 down, decrease the exponent by 1, and multiply it by the derivative within. So this is the first times the derivative of the second, plus the second times the derivative of the first, 5x to the 4th. And this is all over that denominator squared. So if you didn't remember your product quotient chain rules from Calc 1, we certainly got a good workout here. Now this is kind of a huge mess. My recommendation is always to factor, factor, factor instead of trying to go through and start simplifying by expansion. So that's what I would recommend here, is that we simplify this. However, you know, we don't have enough space here and we're running out of time. So remember, simplify to get relevant information. And that would probably take at least another page to simplify this down. It might be kind of fun to do. If anybody simplifies this down, let me know. I'd like to see what it boils down to. But the point is it's very complicated. Now remember, we said we'd look at two cases. So the other way, let's go ahead and try logarithmic differentiation, on this expression. And remember, that was ddx of the cubic root of x squared plus 2 all over x to the 5th times x squared minus 1 to the 4th. Now, with logarithmic differentiation, we have a little bit of a problem before we even get started. In order to use logarithmic differentiation, I have to take the natural log of this. But I can't take the natural log because I have to balance the equation. So whatever you do to one side, you have to do to the other to balance the equation. So what I need to do here is make up the other side. So what I'm going to do is set this expression equal to y. Now it makes sense to take the natural log of both sides. So again, logarithmic differentiation, you take the natural log of both sides. Now the whole idea of taking the natural log of both sides is that I can use all those nice simplification rules to come up with an easier way to take a derivative. So we have natural log of y. I'm not taking the derivative right now, I'm simplifying. So this would be the log of a quotient. The log of a quotient is the difference of the logs. So I'm rewriting using my rules of logarithms. Okay, and again, don't drop the left-hand side here. It's going to be very important. Bring the 1/3 down using my logs of logarithms. Now here, over in this piece right here, I have a log of a product. And remember, the log of a product is the sum of the logs. So this is going to be minus the quantity. And if anybody makes a mistake, it's usually right here by not putting up some curly braces. Because without the curly braces, this negative wouldn't distribute through, and I'd have a sign error in my solution. I can simplify this even further. So I have the natural log of y, and again, I still have not taken a derivative. Now in my last problem, I spent all my kind of the mess on the calculus part. Now I'm spending it on simplification, which is a little bit easier. Pop this 5 out front. Distribute the negative. This becomes negative 4 ln x squared minus 1. And now we're ready to take a derivative. So when I take my derivative, I have the derivative of the natural log of y is 1 over y. Except I have to use the chain rule here, and the derivative of y with respect to x is dy dx. You might remember this concept from Calc 1. It's called implicit differentiation. So I differentiated the left-hand side. Now I'm going to work on the right-hand side. I drag the 1/3 along. 1 over u times the derivative of u. Okay, and so that piece, the derivative of this piece, is right here. Drag along the minus 5. The derivative of the natural log of x is 1 over x times the derivative of x. Drag along the minus 4. The derivative of the natural log of x squared minus 1 is 1 over x squared minus 1 times the derivative of x squared minus 1. And this is my expression. Now I am not done with this. So I'm just going to do one quick little cleanup here on the right hand side, and then we'll try and finish this off. So this looks like 2x over 3 quantity x squared plus 2 minus 5 over x minus 8x over x squared minus 1. But that's not quite my derivative yet. If you look over here on the left, I have 1 over y dy dx. Now remember, I wanted dy dx, so I need to solve for dy dx. And the way I'm going to solve for dy dx is to multiply both sides through by y. But y has to distribute through this entire polynomial, so I need my curly braces up, or some parentheses. And then I can see that I have canceling occurring here, and on the left hand side I'm left with dy dx is equal to this entire expression times y. But we know what y is. Y was equal to this value way up here when we started this problem. Okay, y was equal to this value. So that was x squared plus 1 to the 1/3 divided through by x to the 5th times x squared minus 1 to the 4th. And that's my derivative. It needs some cleaning up too, but I think this was a little bit easier technique to use logarithmic differentiation on this. You didn't have to, okay, but we could have. Now the very last thing I want to talk about in regards to logarithmic differentiation is when you must use logarithmic differentiation. Now notice in the last problem we did, we did it two different ways. we did not have to use logarithmic differentiation. Okay, I didn't have to use it, but sometimes you have to use logarithmic differentiation because I have no other techniques that I can use. So again, sometimes there's no other methods and I have to use log diff. And I have to use logarithmic differentiation to take the derivative of an expression that is of a particular form. And that particular form is a variable expression to some other variable expression. Meaning I have some function of x down here and a function of x down here as well. So some examples would be x to the x. That's it. If I want to take the derivative of this, I have to use logarithmic differentiation. I could have x squared plus 1 to the sine of x, and again, I have to use logarithmic differentiation on this. Another one would be the tangent of x to the sine of x. And again, logarithmic differentiation, tangent of x to the sine of x. So, let's go ahead and look at an example of a problem where I'm actually having to use logarithmic differentiation. So for this example, the first thing I see is, okay, I want to take a derivative, I can't use the power rule. There's not a product, there's not a quotient, there's no chain here, so I don't have any techniques I can use right now. So, no derivative rules will work here. So what do? Well, first of all, I note that this is a variable function. I have some function of x raised to some other function of x. And when I have a variable to a variable, I use log diff. So the steps for logarithmic differentiation are the same as in the problem we did up above. The one we did up above, we didn't have to use log diff. So the first thing I do is I set equal to y. Next thing, I take the natural log of both sides. And then I get to use that nice little rule of bringing that exponent out front. And that basically solves all my problems now. So I have cosine of x, ln of x. Now I can take the derivative of both sides. Left-hand side is implicit differentiation. 1 over y prime, or 1 over y dy dx. Now on the right-hand side I have the product rule. So I have the first function times the derivative of the second. The derivative of the natural log of x is 1 over x times the derivative of x. So again, I have the first times the derivative of the second, plus the second times the derivative of the first. The derivative of the cosine of x is negative sine of x times the derivative of x. And I know you probably don't write out those times ones. I'm just trying to show some extra steps to make sure you see where everything's coming from. So let's go ahead and clean this up. 1 over y dy dx is equal to cosine of x over x, and of course don't you dare try and cancel those x's, minus ln of x sine of x. Okay, to finish this off, I multiply both sides through by y, remembering that y has to distribute. The y's cancel, and I am left with, on the left, what I want. Dy dx, that's my derivative, is equal to cosine of x over x minus ln of x sine of x, and this entire quantity is going to be multiplied through by y. And remember, y was equal to x cosine of x. Now there's some simplifications that we can do here to further this. We could find a common denominator of an x and pull the x out and flip that x up top. But this is my derivative. Now remember, this derivative has all the same definitions of any other derivative we worked with. It's the slope of the tangent line at any point along the graph. We don't use this quite as often, but the derivative of position function is velocity, the derivative of velocity is acceleration, so it has all the same meanings. Make sure you practice logarithmic differentiation problems. They'll for sure show up on quizzes and tests.